room, you think? Couldn't we put us here in the first place? All right. Oh, well, we're here now. That's the important thing, right? Okay. So, any questions? Yes.
So for the program 3,
Yes.
you make files, I want to make 8 o'clock, right?
Mm-hmm.
So if I just say 8 o'clock and then enter, is it still running?
That's how you start it, yes.
When I say 8 o'clock and then I just no argument at all, just say
Right.
8 o'clock,
Yep.
is it still running?
Is it still running? Yes, using your default value for the timer.
So if you're given no hours, minutes, seconds, you ignore that?
You would go with the default timer, yes.
So
But you wouldn't have an alarm clock.
Yeah, that's what I'm wondering.
That's fine.
Okay.
You would not have an alarm clock. You would have the default timer value, and when it counts down, then you would stop the regular clock.
Okay.
Does that make sense?
what
Yeah.
if I just put 8 o'clock and then H and M without S, is it still running too?
No, that's incorrect input.
Okay, so it has to be 3, right?
Yes. Yes.
If we insert the time, like for hours, minutes, and seconds, do we separate those by spaces?
Yes.
Okay.
Mhm.
What if I'm not setting the timer, but then what about the CT? I just say 8 o'clock and then C, the number of CT.
So if you enter in your alarm clock, then and no timer value, then you would use the default value for the timer.
Oh no, the countdown timer.
Mhm.
I'm not set up my alarm clock, but I make my countdown timer.
You
Is it
can't,
still running?
so. Hours, minutes, seconds, countdown timer. Okay, you, a clock by itself. Enter. It will run without an alarm clock,
Mm.
using the default value for the countdown time. If you enter a clock with hour, minute, seconds, and enter, you will run with an alarm clock using the default value for the countdown timer. Or you could have in which case you have your alarm clock and your countdown timer.
What if just countdown timer without alarm clock?
These are the only 3 valid inputs. It's the only way you can do it to know for sure that you have, I'm trying to make your input processing easy. Okay. This is the only way you can unambiguously determine you have an alarm clock and either default or the time entered value.
So those 3, the only one that you're gonna run, right?
Those are the only 3 legal inputs.
What if you have float? Are you gonna
No floats.
test? Okay.
Just integer.
The alarm
Trying
clock.
to make your input processing simple. Yes.
The countdown timer just counts down from whatever number you specify down to 0?
Yep. And I'm not gonna make you do like checking for ranges of integers. You can assume that if somebody entered in a value here that's within range of hours, minutes, and seconds.
So we're not checking for like weird numbers.
Yeah, you're not
Okay.
checking to see if it's larger than 60. You're not checking to see if it's larger than 60. You're not checking to see if it's larger than 24 or anything like that.
So not gonna check if it's string or not, right? It's just integer. Like
So
one,
your
two,
input, yeah, your input's gonna be 0, 3, or 4 integers.
I'm saying that what if you have, you know, the input of a string? No, you can't do that, right?
No, you're gonna read from page, I'm sorry, that's not it too. No, that's the only thing you're gonna get.
But I think he's asking like, do we, because if you enter in like 1A, ATY, or return 0,
Mhm.
are there, like, he's asking what, or do we need to do that depth of like error checking, or can we just assume you're gonna give us integers always?
That's what I just said. You can assume that the input was formed correctly. The operator provided something else, that's bad on them, it's bad on the grader, right? I don't want you to have, I don't want you focusing there, I want you focusing on system calls and that kind of stuff. So everybody knows about argc, right? All right, other questions? Nope, we're good, huh? Oh, okay. Then let's see, where are we? Oh yeah, we're here. We actually kind of got ahead of ourselves because we already talked about these last lecture, in addition to what we were talking about, biodiversity, all that fun stuff. So we'll just pick up from where we left off. Did that, added some DNA. I think this is where we're stuck, isn't it? I think this is the point where I saw lots of heads were doing this sort of thing. People were wilting from the heat and being up all night every weekend, but something like that. Okay. So the software layers, okay, is an abstraction, of course, but it's more than abstraction because when we actually implement the code, each of these boundaries have some interfaces that we can access, some APIs, some system calls that we can make to access any of these different levels of the input-output subsystems, processing layer, okay? Obviously, hardware is what we're working with, right? We're managing hardware. Remember, we're here to be managers, right? Everyone's excited about that. So we have the hardware down here, and the most fundamental thing that we have on top of the hardware itself is the interrupt handlers. Because the interrupt signals are actually on the hardware, the interrupt signal says there's something there, and that's how we're gonna get notified that hardware's actually done work that we're interested in, right? Or at least from an IO's perspective that we're interested in. So right up above it is these interrupt handlers. And we're gonna talk about those because they provide the most fundamental processing for each of these different types of I/O channels that we can have. On top of that, then we have this class of work that we call device drivers, which knows all about the specific details of this particular I/O device. For example, if it was a hard disk system, this device driver would know that, oh, not only is it a hard disk, which means that it has rotating stuff, it has heads that it has to position, it has different ways of forming addresses, its signals for doing the handshake as well as the data transfers are different, data transfers themselves are gonna be different, and all the things it needs to know about that hard disk. And the thing is that device drivers, since we have so many different manufacturers with so many different architectures of hard disks, that we're going to have a lot of different device drivers that understand that specific hard disk drive, that understands its addressing scheme and understands its control signals. Okay, so it's still pretty specific. I shouldn't say still, but it's very specific to each of these different manufactured devices.
What about, like, you know how Windows says they have those generic drivers?
Mm-hmm.
I mean, obviously they would fall in like in that category, but how do they, like, do they program, like, do they provide like an interface that like, hard drives know about, like,
Well, even on Unix and Linux systems, we have some generic device drivers because no matter what manufacturer makes a mouse, they're all implemented on the same standard and are all processing the same way.
so is that, is at the hardware level, like physical devices, they're done so like in a standard way that everybody agrees on?
Yes. Yeah, for that particular I/O communication
Yeah.
path, right? So if I have a USB device, I can have a generic device driver
Or
for a
like
USB
state-of-the-art
mouse.
IDE.
Or that same with IDE, right? So I can have some very generalized ones, and if that particular manufacturer works with default values, so to speak, that generic device driver will work. But many device drivers, they're competing with each other, so they put in features that makes theirs at least sell better, hopefully perform better, right? And so therefore, its device driver is going to have to be constructed so it can take advantage of those unique features that they built into that wonderful rotating device. Otherwise, it couldn't. The generic drivers would just go out there and hit and say spin, give me data, done. Okay. Excellent question. Okay, so all of those stuff will be contained inside the device drivers. Of course, accessing interrupts for that particular kind of device, and we know what the different interrupts are, the different priority levels, and how to respond to them. Then we have this other class called device independent operating system software. What this is really saying is that device drivers are very specific, but there are some things that we do for these devices that cut across all the different manufacturers. Okay, and as a matter of fact, might cut across all of the different subcategories of devices under that one category, like hard disk drive. For example, hard disk drives are going to do block transfers. Okay, so all of the code that handles the block transfers, manages it, pushes data around, knows how to move the bytes one at a time, even though it's a byte block transfer, all that code's gonna be up here. Okay, and some other features as well. That kind of gives you an idea of the types of things that goes in this layer here. If it's cutting across all hardware device, possibly all hard disks specifically, yeah, we'll put it up here. And then, of course, there's your code. Read, write, put, see, get, see, all those fun things. And so they're all going to interact with each other. Now, the fact that we have this designed as layers here doesn't mean that you have to use the device driver that is actually loaded on the operating system. If you want to build an application that takes advantage of some of the special features in a specific hardware device, you can build that yourself and bundle that with your package. And you don't even have to have it loaded in the same place the device drivers are loaded, but you should. You can still use it. And the concepts are the same, however. And the idea with making this kind of construct here is that you can build it once, you can use it many times. When I say use it, different programmers can use each of these different subcomponents, these different layers. Okay, you don't have to reinvent this wheel every single time you build your project. Right? You can use the standard stuff out there if it works for you. Oh, I had this slide. Okay, so yes, more examples of stuff that would be in each of these different layers, which we pretty much talked through all those things before. Some other things in the device independent layer. In addition to the buffering, we also have the error reporting. Now that's not the same thing as a return error value from a system call. This could be additional information about this particular hardware device. So, because at the device independent level, it knows things about, okay, right now I am doing the handshake. If it fails on the handshake, you will then know that, oh, this device driver might reattempt it if this particular device allows that kind of thing to happen, right? So it might do error checking, and it might try to retry the I/O, or it simply might report up the error that, hey, specifically, the device is having issues with handshaking, you've got to do something about that. This layer is also where we would actually try to get the devices, okay? Getting devices, releasing the devices is common across all manufacturers. Now, true, the actual signal in the handshake might be different But that's down at the device driver level. The device independent layer, we're still doing the basics of allocating and releasing, so we'll provide that. And the blocks for the buffering, as we mentioned, and of course, the uniform interface that we're talking about. Open, close, FGET, FPUT, get C, put C, all those things right there, so that you can call them from your application level. And then it's going to translate that, so that it goes down to the next layer for the device driver into the actual machine instructions needed to make that happen. Okay, let's talk about device drivers in a little bit more detail. We talked about the hard disk model because it's pretty easy for us to understand that. But it's really easy to see some of the dependencies when you start taking a look at other classes of I/O devices and you're comparing them. Because even though I may have a lot in common in the sense that, yes, I can generate output. Well, I could generate output, but a device like this, I probably am not gonna do too much output, right? It's probably gonna be mostly input. A device like this is probably almost all input, unless it's a read-write. But it's in read-only, so it's not, right? So it's gonna be all input. This is gonna be all output. This is gonna be all output. Right? Except for the handshaking stuff, the data itself is flowing in one direction. Okay, so that in itself says, these things are very different. Also look at the data rates. The data rate between this and this is very different, right? And, the other thing is, this is going to be a stream-oriented device. This is going to be a block-oriented device. Right? We're transferring blocks of data from our CD controller into our system, and here we're going to be sending out a stream of bytes to the printer device itself. So we have some very different ways of managing or using these I/O devices depending upon what its purpose is. And that's going to drive our device drivers design quite a bit. Yeah?
So a question, so how would kernel modules fall in this category? Like do some device drivers install kernel modules? Like things like that, or is that like totally separate?
Totally separate.
Okay.
Device drivers are laying in the file system and get loaded whenever that I/O device is needed, and unloaded when it's done. Okay, so again, a lot of this is notional because the implementation has to deal with buses and all that kind of good stuff. But the concept that we're trying to get across here is that we have some devices that are input only, some that are output only. Some of them are both. Some are block oriented, some are string oriented. And what's, of course, controlling all of this is your user code up in the application code space. But it has to transfer the bytes to or from kernel space. And at that point, you have to be in the kernel mode, and at that point, you are going to be using system calls, which is part of the operating system, bringing in parts of the operating system to do that work for us. So I have to move data in and out of kernel space and user space, depending upon what that device is doing. The device driver now, its job, because that's what we're going to focus here, in the kernel space, this device driver, you'll never see it here up in the user space because we have that device independent layer between the two, right? We made that system call in the device independent layer. We provided the buffer and the page sizing so that we could transfer that data from one space to another. And now, the rest of this is down here in user space except for the hardware, right? Because that's underneath all this stuff. So the device driver now has the data here in kernel space so that it can either move streams, bytes at a time, or blocks at a time to that particular device. Worrying about things like what sizes of data can I transfer, right? In a stream-oriented device, it's only worried about what's my rate of transfer for my bytes, it's my streaming bytes. Here I'm worried about my block size and whether or not I can stack up blocks, because some buffering techniques will let you do just a page at a time. Some will let you actually stack up and queue your pages for being able to transfer one right after the other. Is there any questions on device drivers? Talks about things that they can do. They're specific to that class of device. We can have generic ones for some classes. Some classes we have to have particular ones because it's very unique. But in a lot of cases, generic still will work. Got it? Questions? Ready for interrupts? Okay, ready for interrupts. You got it. All right, so interrupts. As we mentioned before, something happens on hardware. It wants to tell the operating system that something's done or acknowledge that something has started. In most cases, it's something has done. In your assignments, you're going to be working with interrupts quite a bit, right? Because you're going to be working with signals, which is an interrupt. It's going to use interrupts. Right? We talked about different levels of priorities for interrupts. We could ignore some. We could pay attention to all of them. Okay, so we need to understand interrupt handlers better than to get a better appreciation of how all this is going to work. So what's going to happen with an interrupt, whether it's a clock interrupt, whether it's a countdown timer interrupt, which is really a clock interrupt, because what you do with the countdown timer is you are setting up an event to happen in the future, some number of seconds in time. And what will happen is when the clock reaches that particular event in time, or time rather in the system, it sees that there's an event registered. The event is your signal to wake you up. And then it'll raise an interrupt at that time. When it raises an interrupt, a process is currently running. There's always a process running, right? So there's a process running. But your countdown timer went off, or your time of day clock went off, or your alarm clock went off, and you got this event that you want to process, so the system raised an error. And the running process then is going to have to save the current registers, although in some systems the interrupt hardware itself will actually save those registers for us in a single CPU operation, so we don't have to do extra work. But not all hardware does that. So if that doesn't happen, then you have to have some operating system code that will save the registers and then prepare for a context shift for the interrupt handling routine. Okay? Depending upon the interrupt that was raised, we need an interrupt handler to handle that particular interrupt. Why? Because every different interrupt type has different work we need to do. In this particular case, we had an event, right? We registered for an event. We wanted an interrupt to come and let us know that a certain time was reached. So in that case, it's going to go to the interrupt handler, which knows how to find what process registered for this type of interrupt. So there's some good code in the interrupt handler. Why is that important? Because every handler is different size. Right? Not all work for every different type of interrupt is going to be doing the same thing, therefore it's not going to be the same size. However, when we create our operating system in memory, we need to know some very specific addresses. Okay, depending upon where in memory your operating system gets loaded, a lot of times it's towards the end. Since the hardware is calling the system, the hardware has to know what address to go to. So at some address, it has been determined that you will have an interrupt table. I'll expand this address like this. Okay, so starting at this address, there's going to be an interrupt table. I also need to know what the length of this interrupt table is, because there's other code that's going to be loaded up after this table and so on. So what that means is that I have to predetermine the size of this interrupt table and what every address in here is. So what most operating systems will do is they will simply say This interrupt table is simply a jump table. Okay? So we said before, right, last lecture, we said that I might have like 16 predefined interrupts, although 2 of these types might be programmable, right? So I'm gonna have something like 16 predetermined interrupts. So I create an interrupt table that has length of 16. And inside of here, what I'll do is I'll have the address of where the interrupt handler is for interrupt 0. And then I'll put the address the starting address of interrupt 1, and so on. Because what I can do is, as I'm creating this operating system, and it's going from a file, a program file that contains the compiled code for the operating system, but I'm starting to load up my operating system, including places in memory for specific routines of the operating system. One of the specific addresses I need is that of this interrupt table that needs to be fixed so that the hardware can get to the interrupt table in any one of these addresses for any one of these interrupts if they should be raised. And since I'm using a jump table architecture, the handler for that interrupt is going to know that if I go to this address, this contains the address of the device driver. So as I'm setting up for my context switch here for the interrupt handler, I get the address, the starting address of the interrupt handler, and then at runtime, it can get loaded up wherever I want it to be loaded up, I being the loader, and then I can just simply put this address into the jump table at this location here, and now the hardware knows where to go. Okay? It's always going to go to this address, relative offset to the start of the interrupt table, relative address to the interrupt 2, and that contains the address for my interrupt handler routine for that interrupt. We now have whatever code, whatever length it needs to be. Okay? Yes?
So you said those, the address of the interrupt handlers are like they're determined during runtime? Are they like?
As you're loading,
As you're loading?
yes. As part of the loader routine is to populate memory with these different structures, in this case here, my interrupt handlers, and then populate the interrupt table with the start address of each of the handlers. Okay? So now I can go from here to here because I can get into my interrupt handler. And what I'll do is, of course, finish the context switch by putting a stack for the interrupt handler routine itself to work with. Acknowledge the interrupt controller, which is the CPU saying, acknowledge that interrupt so the next one can come in. And then re-enable interrupts. Copy registers what I've done from where they were saved to the process table. Now this routine can start doing its work. When it finishes its work, if it's recoverable, that'll be part of the code. Remember, some of these interrupt handlers are not recoverable, right? Like 0, bus fault. Remember that one? Bus fault, divide by 0, all that kind of stuff. Memory out of range, another one. Non-recoverable errors. Well, actually, memory out of range, we can handle that one now. But for a while, we couldn't. So if it's not recoverable, it's going to shut down the operating system itself. But most of them are recoverable, in which case it will have logic in here to select the next process to run, and then set up the MMUs so that the process can get, by restoring its context from the process table for that particular process it's selected, restore the registers with that process's context, and then that process starts running. Because you know, just as soon as you do this, you're not doing anything more, right? This is automatically happening as soon as you do this, right? Because one of the registers is the so you're not going to ever do this because you're actually changing that control to the new process when you do step 9, because one of the registers is the, what register? Program counter. And the program counter is just gonna go fetch the next instruction, which you just put into here, right? So, there's no work here. You're automatically doing that when you finish, that's part of number 9 here. Okay? So interrupt handlers, that's what they're all about. Any questions? Interrupt handlers are a big deal. Got it? Okay. Okay, so let's take a look at our Unix and Linux systems the same. This part of the architecture is the same. All right, so we're looking specifically at the file subsystem here, subsystem, right? So part of the file subsystem is the stuff that we were just talking about. The code for the device independent code is going to be up in here. Okay, and then depending upon whether you're doing character or string-oriented I/O versus block I/O, means that you may or may not have this buffer cache between the file subsystem and itself. Because remember, I have content that I'm trying to get in and out of the file subsystem, and I'm trying to get that in and out of the rest of my system, right? So I'm gonna have this cache if it's a block-oriented transfer. If it's string-oriented transfer, it's going to notionally go straight through. Now, I say notionally and emphasize that because a lot of implementations today actually have some form of caching going on here, certainly some form of buffering going on here. This has buffering going on as well, and that's just like the name implies, buffer cache. Right? So a lot of systems today have buffering going on in here. But notionally, it's straight through. And then talking to those byte streams or block streams of device drivers themselves. So let's take a look at buffering. Okay, let's look at some old modem technology here, which modems are still in use. You actually have modems in your laptops and these things too, right? Communicating to some sort of wireless network. So here's how you could do buffering. Okay, so in this first case here, okay, you have, obviously you want bytes to go into or out from your user process. You could notionally just take it straight from your process here to the modem itself. No buffering, not even going through kernel space, just going straight out there. Well, that's kind of ugly, right? Because first off, I always want all of my data to go through kernel space. I don't want to let any user process talk directly to hardware devices. Because as soon as I do that, I lose all security. I lose all control of ensuring the integrity of everybody's process and data from each other. And somebody can easily take control of the whole system if I allow any user space to directly access hardware of any form. Okay, so this notional diagram, let's get away from that concept and let's say, okay, it's not buffering it, but it's still going through the kernel space. Okay, so it's really still transferring it to kernel space, and it's the kernel space, and it's the kernel, this routine's running in kernel mode that's actually transferring data in and out of the modem. Okay, so that's what the diagram was really trying to say, but a lot of people don't interpret that way. So I want to make sure we understand that this is still moving it into kernel space, but the kernel space is not holding on to it. It's not buffering it. It's just an immediate out or an immediate in. Okay? Got that? It's immediate out, immediate in. So another concept that we could do is we could create our own buffers in our user code. We do this, well, I think we do this all the time, right? Don't you write buffers when you're doing your inputs, outputs, and stuff? So a lot of you will do that. you can create your own buffer space up here in the user space and manage it that way, but then when you move it out to the device or in from the device, you're not having the kernel space doing any buffering for you. You want it moved instantly, directly, non-buffered. Okay, so that's a second mode that you could use. A third mode would be to introduce a buffer inside a kernel space itself. What this allows us to do, it allows our process in user space to operate more asynchronous with the hardware than we were doing in non-buffered, right? In this space here, we were blocking for those transfers. Until that transfer completed, my process wasn't making any progress. It was waiting for that I/O action to complete. But here, I can now disconnect the two. I can pass data through or pass data in through this kernel space, and I can detach my process from it because I now have a buffer here, I have a buffer here. As long as the buffer is not empty or full, I can let these be independent. Once one gets full or empty, then there's a dependency on the other one. See that? So that's going to be an issue with this design, is that it'll work as long as I can guarantee that this one will never be full and waiting on the process to come back, or that this one's empty, or that this one's full when this one's ready to start sending data as well. That's not good either. So to solve that, because we want our processes to be asynchronous, and we don't want to have to worry about conditions where I might lose data, right? Because if this buffer is full and more bytes are coming in from the modem, what's it going to do? Buffer overflow. Or you just set it up to start losing bytes. Starts dropping them. Oldest first, right? Neither one of those are too good, right? So to avoid that, we come up with some alternative buffering strategies like this one here. And what this is saying is that the kernel space is going to use one buffer. When this buffer gets full, it's going to interrupt this process to say, hey, come and service this buffer. In the meantime, it'll switch the input device to a second buffer. And it'll start filling it up, but the idea is that the user process can come around and empty this buffer before this one gets full. That way when this one gets full, I can then switch it over to this one, and I can just keep alternating between A and B buffers. And then when the process comes back, it just empties the one that was just filled up, and then when it comes back, it gets the next one that was filled up, and so on. That way I always have a buffer available for a modem to write to. And I can have my asynchronous design that I so much want, right? So the other thing, and if you didn't understand this about modems, is that modems have absolutely zero control over the data coming into it, right? Data's coming in at whatever rate whoever's generating data for it is generating it. And the modem's job isn't to worry about the operating system. The modem's job is to take whatever wireless or wired network it's connected to, take that input stream, and give it to the operating system, have a nice day. And so that's why these buffers are really kind of important. Okay, so another model that should interest you as well, it's using the same basic technique, but it's talking specifics now to network layers, okay? So that's something everybody understands. They plug their laptops or desktops in to talk to networks, or you turn the wireless receiver on, which is the modem, right? And doing that model. So it's pretty much the same concept, except that if you're working with a physical network, typically the network controllers have their own buffers as well. Okay, so you might have an additional buffering scheme if you're working with a physical network model. Although yes, some software modem mix processors are doing that now as well, but that's the idea, is that some will, some won't. So in the case of having a a buffer inside of your network controller itself almost gives you that two buffer option, except that now the kernel routine and device driver, as well as the controller itself, has to manage these buffer spaces themselves, in which case you might want to still consider an AV buffer model in your kernel space, even though you're talking to a buffer on the other side of the hardware. Okay, now it's more complex because in a network model, in most network models, not all network models, but most network models, certainly packet switched models like IP is, you may have multiple copies of the same same packet. You might have multiple copies of the same packet because sometimes these network controllers will send out another copy because it didn't get an acknowledged back saying that the packet it had sent out earlier actually got received. In which case they'll try to resend it. In which case you're actually putting more data on the line than what you originally planned to do, because you're putting multiple copies of some of the packets out here on the network. And one of the things the network controller is doing is it's looking for duplicate arrivals. So if it sees the arrival of a packet that it already received, it throws it away. Okay, so there's additional processing on an IP switch-based packet network than there is on standard modem communications. So the buffering schemes here tend to also get a little bit more complex, because if I'm dropping a packet that's in a buffer, I'm going to have to then manage the buffer a little bit more smartly than I am in a straightforward scenario like I talked about previously. Okay, so this is going to be a little bit more complex because of that reason. Okay, so any questions on buffering? You think we got it? You scare me. Sure, we got it. Okay. All right, so now let's talk about disk architectures again. Okay, and I know we talked about them at a higher level before, but now let's take a look at some specifics, okay? When we talk about a disk architecture, we're talking about all of this stuff, because the physical model is going to be broken down into a logical model so we can form addresses where we can use as much of the disk as we possibly can without making the addressing schemes too complicated. Sounds complicated, doesn't it? It is, right? Because the problem with disks is that there's a lot more bytes here than there is here. Right? Remember that geometry class you took a couple years ago? It still applies. So yeah, we can fit a lot more bytes here than we can here, and we're going to come up with a simple addressing strategy that can deal with that, right? Okay, how about a trade-off one? Yeah, because we don't want to waste bits, but we know we are going to. So we want to minimize the number of bits that we waste versus the complexity of the addressing scheme, right? We're going to try to find that sweet spot where I'm maximizing both of those as much as I can. So what we did is we decided to come up with these concepts of cylinders, tracks, sectors, and then bytes, okay? So we're going to design our disk architecture such that they're divided up into cylinders, and each cylinder is going to be divided up into tracks. Each track is going to be divided up into sectors, and then each sector will have some number of bytes that it can then manage. Okay, and you can see some notional numbers over there for something that you probably haven't seen a floppy disk, most of you, right?
Not that.
I know, some of you have, but I think some of you have probably not even seen one. I guess I should put that in my bag too.
5-inch ones.
8-inch Promencos.
I'm not that old. I'm old enough for the 5-inch
The
ones.
5 1/4.
Yeah, I'm more older for those.
You remember 5 1/4, some of you remember 3 1/2. Anybody remember the 8 1/2 Promencos?
I think I've seen them, I just never used them.
Yeah, I used one.
Yeah, well, I think my grandpa has them from like old DOS-based systems, or even like before DOS. Anyway, I
Yeah,
digress.
So get the idea is that, yeah, we have these things called floppy disks that he's still using as a fun comparison to a really small hard disk. Okay, so that's how we're gonna divide our architecture up. We'll take a look at that more here in a minute. And disk capacity obviously is going to be a function of how many bytes we can effectively address from the physical real estate we're given in this hard disk. Okay, that's our trade-off value. Right? We probably get more if we come up with a more complexing scheme. We can get more if we come up with a more complex addressing scheme, but it becomes too complex to be effective. So that's the best we can do now. Of course, on a solid state drives, much better, 100% usage, got it. As well as reliability, got it. But these are still cheap, so they're gonna be around a while. So given that they spin, they also have delays, right? And we're gonna look at these, actually we've looked at these a little bit, but we'll talk about these more in detail. Seek times, rotation times, and some disks are spinning continuously, some disks